Welcome to this video where we will be addressing the concept of inverse Z transform. The inverse Z transform. Given a function x of z, the inverse Z transform of x of z is going to yield the corresponding time sequence x of k. And therefore, by the inverse Z transform, we need to obtain the corresponding time sequence x of k given a function x of z. The notation that we use for the inverse Z transform is Z inverse or Z power minus 1. There are a number of methods we can use for obtaining the inverse Z transform of a function x of z. And in this video, I'll be looking at two of them. One, which is the direct division method. And number two, we look at the partial fraction expansion method. So we look at the two methods one at a time. The first one is the direct division method. Any function x of z is, or the Z transform of a function is obtained as x of z is equal to the summation k is equals to 0 to infinity of x of k, z power minus k. That means if we carry out the division of x of z, we divide the numerator polynomial in z by the denominator polynomial in z, we obtain a polynomial in z inverse. The expansion of x of z from this formula can be written as x of z is equals to x of 0, z power 0, plus x of 1, z power minus 1, plus x of 2, z power minus 2, plus x of 3, z power minus 3, plus all the way to infinity, which we can write as x of 0 plus x of 1, z power minus 1, plus x of 2, z power minus 2, plus x of 3, z power minus 3. That means given x of z is a numerator polynomial in z over a denominator polynomial in z, upon dividing n of z divided by d of z, then we end up in a polynomial in z inverse with the coefficients x of 0, x of 1, x of 2, all the way to infinity. That means if we can perform the direct division of the numerator to the denominator polynomials in z, then by looking at the coefficients of the polynomial in z inverse, we can obtain the corresponding x of k as the time sequence for our given z, that is z transform x of z. Let's illustrate this with an example. We take an example. Now, given a function x of z, which is equals to z divided by z squared minus 3z plus 2, we are to obtain the corresponding x of k using the direct division method. So when we carry out the division, we'll obtain z divided by z squared minus 3z plus 2. So when we divide, we'll get z power minus 1, so that this is z minus 3 plus 2z power minus 1. And this is going to yield 3 minus 2z power minus 1. Next, we multiply this by 3z power minus 2 to get 3 minus z, 9z power minus 1 plus 6z power minus 2. Again, upon subtraction, we'll get 7z power minus 1 minus 6z power minus 2. Then again, upon division, we multiply this by 7z power minus 3 to get 7z power minus 1 minus 21z power minus 2 plus 14z power minus 3. This will give us 15z power minus 2 minus 14z power minus 3. Then again, we multiply this by 15z power minus 4 to get 15z power minus 2 minus 45z power minus 3 plus 30z power minus 4. And as you can see, if we proceed, we can write our x of z as x of z is the polynomial in z inverse as z power minus 1 plus 3z power minus 2 plus 7z power minus 3 plus 15z power minus 4. Of course, plus all the way to infinity. Then we can compare these with x of z, which is x of 0 plus x of 1, z power minus 1, plus x of 2, z power minus 2, plus x of 3, z power minus 3, plus, as obtained previously in our previous equation, from which then we can realize that x of 0 is 0, x of 1 will be 1, the coefficient of z power minus 1, x of 2 is 3, the coefficient of z power minus 2, x of 3 is 7, x of 4 is 15. Okay. From which our x of k, if we look at the relationship in terms of x of 0, x of 1, x of 2, x of 3, and x of 4, we can obtain that for any given value of k, x of k will be given by 2 power k minus 1. So x of k, we're saying is 2 power k minus 1, such that when k is 0, then this will be 2 power 0 minus 1, which is 0. When k is 1, we'll get 2 power 1 minus 1, which is 1. X of 2 will be 2 power 2 minus 1, which is 3. X of 3 will be 2 power 3 minus 1, which is 7, which are the corresponding values of x of 0, x of 1, x of 2, x of 3, and so on. And therefore, the corresponding inverse z transform for our given function is given by x of k is 2 power k minus 1. And that is the inverse Z transform using the direct division method. In the second method, we look at the partial fraction expansion. Partial fraction expansion. In partial fraction expansion, we first put the function x of z into its partial parts and then obtain the corresponding inverse z transform of the individual partial fraction parts. And this can be done using the Laplace transform table. Let's take the example that we have just handled, and we handle it using the partial fraction expansion method. So our function was x of z is z over z squared minus 3z plus 2, which can be written as z over z minus 1 into z minus 2. We look at the factors of the denominator, which we can write as a over z minus 1 plus b over z minus 2. For ease of expansion, we get our x of z over z first. We expand it in partial fraction form, and then once we have the partial parts, we multiply all of them by z. Our x of z over z can be written as z over z squared minus 3z plus 2 multiplied by 1 over z, which is 1 over z squared minus 3z plus 2, which can write in partial parts as a over z minus 1 plus b over z minus 2, having the factors of the denominator being z minus 1 and z minus 2. Where a will be the value 1 over z minus 2 when z is equal to -1, and this one will give us -1. And b is the value of 1 over z minus 1 when z is equal to 2. This is when z is 1, positive, and this one will yield 1. From which then our x of z over z can be written as 1 over z minus 2 minus 1 over z minus 1, from which x of z will be equal to, we multiply both the numerator and denominator by z to obtain z over z minus 2 minus z over z minus 1. If we divide both the numerator and denominator by z, we can write this as you can write this as 1 over 1 minus 2 z power minus 1 minus 1 over 1 minus z power minus 1. Then using the inverse transform, that is the z transform tables, we can obtain the corresponding x of k for each of the partial parts as follows. So given our z transform table, if we look at number 18, a power k corresponds to 1 over 1 minus a z power minus 1. So we have a power k corresponds to 1 over 1 minus a power z power minus 1. And also, we look at number 3. One over 1 minus z power minus 1 corresponds to 1. So we have this as one of k corresponds to 1 over 1 minus z power negative 1, from which then we can write our x of k to be equal to, then this will be our a. We compare these, our a will be 2, therefore we can write this as 2 power k and then minus 1, and that becomes the inverse z transform of the polynomial x of z using the partial fraction method. And that is the inverse z transform using the two methods, the direct division method and the partial fraction expansion method. Otherwise, thank you for watching this video, and that is the end of my presentation.